Enthalpy. It's a word you'll only hear in chemistry, and it simply means chemical energy. So when reactions take place, there will be an energy change, of course, in the form of heat. So no reaction is going to take place without any energy change. So you can start with the reactants of the reactants with certain amount of energy, and then you end with the products with that same amount of energy. That's not going to happen. There has to be either an increase or a decrease in the energy of course, what you started with. So finally, we get to talk about heat in the context of chemical reactions. So enthalpy is defined as chemical energy that results from the heat flow and chemical changes, reactions at constant pressure. And of course, it helps us relate change to the chemical reactions, as I said. So if we pay attention here, if you remember, these are reactants. Well, we've been talking about initial and final, then these would be our initial state, because we start with reactants. And these are products, so what do you think they will be? They will be our final state. Now, enthalpy is given this symbol, delta H, or the heat of the reaction. Enthalpy is the reaction, Rxn, or sometimes it's written, if you ever see it, delta R, H, means the delta H of the reaction. R stands for reaction, either one. So of course it's going to be the products minus the reactants. Now, this is called the thermochemical equation. Thermochemical is, again, if you have the balanced equation with the associated enthalpy change. This is called the thermochemical equation. Now, some important things to remember is that if we get a negative, this could only mean, if you recall, that the H of the products, or the energy or the heat of the products, is less than the heat of the reactants. Which means this is an exothermic process or reaction, Rxn. Once again, it means heat is lost. If we get a positive, then this could only mean the reverse. The H of the products is greater than the H of the reactants, which means heat is gained. Of course, we're talking about the system. A few important things to remember, because we will be dealing with these from now on, is that the sign of change in heat indicates what type of reaction. So again, if we have a negative, that means it's exothermic, or if it's positive, it's endothermic, and you should know what these mean, as we said here. Coefficients indicate the amount in moles. We already talked about that before. The phases of the reactants are very important. While they're not shown in this generic equation, they will be shown as you see next. Assume the change of heat exists at room temperature, which is 25 degrees Celsius, and that's what the delta means here. So let's talk about some rules that govern these thermochemical equations, and they are very, very important, so please pay attention. It says enthalpy is an extensive property, meaning it depends on the amount of substance. You have more substances, you have more heat released or absorbed. Makes sense. So the magnitude of delta H is proportional to the amount of reactants consumed in the reaction. Meaning, in this case, if we look at this equation and it says to you delta H Rxn reaction, the heat of the reaction, enthalpy of the reaction is negative 890 kilojoules. So this right away should tell you that this is exothermic. Which makes sense. That's burning uh, natural gas. When you cook something, it releases this much heat. In fact, that's why we use this reaction. But what does this mean? It means, okay, you have 1 mole, 2 moles of oxygen, 1 mole of methane, 2 moles of oxygen, 1 mole and 2 moles of water. And this gives you negative 890 kilojoules. Remember, the negative means released. If you double this, make these 2 moles, make these 4 moles, 2 moles, 4 moles. Then what do you think happens to this? It also doubles, so that would be 2 times negative 890. Which would be, of course, negative 1780 kilojoules. The next one is very, very important, is that the enthalpy change of the reaction, delta H, is equal in magnitude but opposite in sign to delta H in a reverse reaction. Look what I did here. This is the reverse. If I reverse this reaction, I get positive 890 kilojoules. Because remember, that same amount of energy now is put back in the system to go back to the reactants to say that. So look what I did is that I reversed this reaction. Now I have the reactants as products and the products as reactants.